Hello, students. Welcome to the seventh session of our second module. Our second module was dealing with isentropic flow. So, two devices that use isentropic flows are nozzles and diffusers. And in particular, in the syllabus, you were asked to study the performance of nozzles. So, there was a topic called operation of nozzles under varying pressure issue. So we have already determined the equations, mathematical equations or expression for mass flow rate with respect to pressure ratio. Pressure ratio means some P by P0. This P can be a particular pressure at any of the sections in that nozzle. So here we are going to explain that particular equation practical, its practical application, how practically this mass flow rate, Mach number, etc. changes with the pressure ratio. Okay, so students, suppose this is a convergent nozzle. So our discussion here is that we are what are we discussing here? We are discussing the performance of the different type of nozzles based on pressure ratio. This nozzle can be either convergent or convergent divergent. Convergent divergent. Okay. Now first we will study about behavior of convergent nozzle. So we have a nozzle here. Okay. So we have a nozzle here. So this is the reservoir condition, velocity equals 0, pressure P0, temperature T0, or density rho 0, and enthalpy H0. So reservoir conditions are nothing but stagnation condition itself. So this is a convergent nozzle, and this the flow is getting exhausted to a chamber where the pressure is PB. So what is PB? PB is back pressure. PB, we call it as back pressure. Back pressure. Okay, so this back pressure can be adjusted using a valve. So if we are able to adjust the back pressure of this space or of this chamber to which the flow is discharged or ejected, then how the performance or how the mass flow rate inside the convergent nozzle changes with respect to adjustment in, or with respect to the variation in back pressure. That is what our main area of study in this particular session. So students, according to the according to the value of the back pressure, or the pressure of the space to which the flow is discharged, the mass flow rate varies. That is very important, because we have already studied that P based on P by P0. P means exit plane. In the equation we use the pressure ratio P by P0. P will be equal to back pressure. Okay, so we are changing back pressure here. So to begin with, suppose here you can see here a figure. What is this figure? This figure is nothing but, this graph is nothing but pressure versus distance. Distance means along this distance. So distance x equal to 0 means it is at the reservoir or entry or inlet of the diffuser. Distance, this particular distance is nothing but the exit plane. Okay, so along the length of the nozzle, how the pressure varies, and third one is along the length of according to the pressure, according to the back pressure, how the mass flow rate varies. So these are the content of study in this particular session. Students, we will start with back pressure. So initially, let the initial back pressures, actually we are varying the back pressure. Okay, so here the y-axis is back pressure. Actually, let the initial condition, let the back pressure PB be P0, or let the back pressure be equal to the reservoir pressure or stagnation pressure. So what will happen? So here also P0, here also P0, which means there is no pressure differential. That means there will be no flow, right? If there is no pressure differential, means there is no flow through the nozzle. So you can see here, initially the pressure is P0, and then pressure inside the nozzle will be P0 everywhere. At any length in that particular nozzle, the pressure will be same P0 itself. So P0 will be constant throughout the length of the nozzle. So you can see that throughout the length of the nozzle, the pressure will be P0 itself, right. And what will be the mass flow rate? Since there is no flow, since there is no pressure differential, there is no flow. So corresponding to P0, the mass flow rate will be 0. Now, now just in order to start a flow, in order to initiate a flow in the nozzle, what should be done? What should be done? You have to just open the valve. Open the valve means you have to decrease the back pressure. So if you decrease the back pressure, so back pressure is decreased below, or decreased below P0, means a flow will be slowly initiated, right? A slight decrease in back pressure induces a flow through the nozzle. The flow rate through the nozzle will be such that the nozzle exit plane, the nozzle exit plane pressure PE will be equal to, so PE will be equal to PB. That PE means the pressure along this exit plane. Pressure along the exit plane of that nozzle will be equal to PB, back pressure itself. Okay. So when then PE will be equal to PB, and there will be a slight pressure differential. You can see that along the length, pressure get reduced. At the inlet it will be P0, and it will be slowly reduced from P0 to PE up to the exit plane. Okay. So pressure will be reduced along the length of the nozzle. So at the exit plane, the P at the exit plane, so here it will be P0. Suppose this is some 5 bar, and the PB is 2 bar, means here at the inlet it will be 5, and after that at a small distance from the inlet it will be reduced to 4.5, 4, and at the exit plane it will become 2. So it will be slightly decreased along the length. So that is the idea. Okay, have you understood that idea? The pressure, you can see in this graph, the pressure slowly decreases from inlet towards the exit plane, and the exit plane it will be reduced to the value of back pressure. So PE will be equal to back pressure. And what will be the Mach number? Mach number will be less than 1. Mach number will be less than 1. Flow is subsonic. Flow will be subsonic only. Okay. So the flow will be subsonic throughout the nozzle, and the Mach number and what will happen to Mach number as the pressure is decreased along the length, means velocity will be increased along the length. So maximum velocity or maximum Mach number will be at the exit plane. Okay, but still the Mach number will be less than 1 only. Okay, the flow will be subsonic only. Now and what about the mass flow rate? Mass flow rate, you can see the second one is here. So mass flow rate slowly increases as the pressure is decreased. Mach number slowly increases. Similarly, again the third one, you can see that again as the back pressure is decreased further, the mass flow rate, you can see mass flow rate again increases, and the pressure distribution of the nozzle changes as shown in the figure third. So in third figure you can see that pressure, a decrease in pressure, a much more decrease in pressure can be seen in that particular third curve. Okay. Now uh, when the back pressure is reduced to a value lower enough to make the exit plane Mach number equal to 1. So I am reducing PB to a value lower enough to make Mach number at exit equal to 1. So I have reduced the back pressure to a very low value such that the Mach number at exit plane becomes 1. Okay, so that particular that particular mm, PB can be represented as PB star. That particular back pressure is nothing but PB star or P star. Better you write it as P star. So you can see here the fourth curve. You can see that it has reached the pressure P star. When it has reached the pressure P star means the Mach number at the exit plane is Mach number at the exit plane is 1. That the flow has become sonic at exit plane means it has reached P star means the maximum mass flow rate has achieved. Okay, the maximum mass flow rate is achieved in that particular. So this exit plane is the region where the area is minimum. So if the Mach number at minimum area becomes 1 means the flow has choked. So ME is equal to 1 means flow is choked and the back pressure corresponding to that particular value is P star. That is P exit plane pressure will be equal to PB is equal to P star corresponding to the choking pressure. Okay. So any further decrease in pressure, you can see here, any further decrease in pressure will not change the Mach number at the exit. ME will remain it as ME, the Mach number at exit plane will remain as 1 itself, and mass flow rate won't decrease because mass flow rate has become the maximum. No further increase in mass flow rate will happen because the flow has already choked. Choked means maximum mass flow rate is achieved. So mass flow rate remains at maximum value even if the back pressure is reduced further. But important point is PE also reached the minimum limit, and if further PE has reached minimum limit and it will be equal to P star only. Any further decrease in PB means PE equal to P star will be greater than PB. Okay. So you can see here PE will be greater than PB only, and if we go on reducing PB means PE and PE won't change, but PB will be less than PE only. Okay. So an expansion. So now the from exit plane from the pressure at the exit plane is higher than back pressure means the flow is getting discharged from a higher pressure to lower pressure, so there will be an expansion wave. So that is represented here. So you can see here, since P greater than PB, there will be an expansion wave happening here. That pressure expansion wave is shown in the fifth curve. Okay. So mm, that is how that is how back pressure affects the performance of a nozzle in a convergent nozzle. Okay. So another point to remember is that suppose this is my nozzle, uh, convergent nozzle. If PB is greater than P star means before choking the discharged particles or discharge stream will be parallel. They will be uniform stream. Okay, they will be a uniform parallel stream. Suppose if the nozzle is discharging when the back pressure is less than P star, that is choking pressure, the stream won't be parallel. Discharge stream won't be parallel. When the back pressure is less than the nozzle exit pressure, the jet expands. As you have seen, you can see here an expansion wave is here. So there is the wave expands as it discharges from the nozzle. The pressure of the jet leaving the nozzle is equal to the critical pressure, which will be larger than P will be equal to P star, and it will be larger than PB. So the sudden reduction in pressure outside the nozzle causes the gaseous jet to expand, creating a pressure reduction in the core of the jet. So in the core of the jet, there will be a pressure reduction, and it tries to reverse the direction of gas particles. That is why it won't be parallel anymore. So there is a complex process happening when PE is greater than PB. Uh, when PB is greater than P star, there is no such complication. The discharge jet will be parallel stream. But when PB is less than P star, means there will be an expansion wave. So it won't be parallel anymore. So that thing you have to keep in mind. Okay. Now we will move to convergent divergent nozzle. So convergent divergent nozzle. So in the previous case we have studied convergent nozzle. Now we are going to learn the behavior of a convergent divergent nozzle with respect to the back pressure. So let a convergent divergent nozzle fitted to a reservoir having a constant stagnation condition P0, T0, H0, exhaust sorry exhaust into a region where back pressure can be varied. So this back pressure can be varied. So we are discharging the flow to a region where back pressure can be varied with the help of a valve or anything like that. So let the AT and AE be the nozzle, throat and exit area. So this area is AT and this area is AE. So AE means exit area, AT means throat area. Okay. So the pressure distribution along the nozzle for different back pressure can be seen in this particular figure, and the corresponding mass flow rate here. So let us try to explain the behavior of the pressure along the length of the discharging nozzle and the mass flow rate with respect to the back pressure. So initially, as the same case in that nozzle convergent nozzle, you can see that when PB equal to P0, when the back pressure is same as reservoir pressure, there is no flow, and is shown in this particular. So the pressure will be same throughout the nozzle, and the corresponding to that pressure the mass flow will be zero. There won't be any flow. But when the PB is less than P0, that back pressure is slightly less than P0, then the flow in the nozzle is similar to what a flow will be initiated, right? A flow will be induced in that passage, but what will be you have already learned before choking the nozzle. Convergent divergent nozzle acts as venturi, very important. So when PB is slightly less than P0 means this passage acts as a venturi passage. The flow may be treated approximately as incompressible. It may be treated as incompressible. So the corresponding pressure distribution can be seen in this particular second figure. So you can see in that second figure means here. So you can see that the pressure slowly, because this part actually acts as a nozzle, it increases its velocity and the pressure gets reduced, and the pressure get reduced to a particular value here, And when it reaches the throat, you can see that after throat the area is getting increased, but Mach number is still less than 1. When Mach number is still less than 1 means the flow is still subsonic. For a subsonic flow, a divergent area acts as diffuser means pressure gets increased, so pressure gets increased to that back pressure, PB. Okay, so that is why the this flow, this passage, now when PB is slightly less than P0, Mach number along the length is still less than 1, and the passage acts as Venturi. And again pressure, the back pressure is reduced further to a value corresponding to this third case, okay, or the second case, wait, second case, value less than P0, but Mach number is still less than 1, so pressure slowly get decrease up to throat, and after throat it acts as a diffuser, so again pressure gets increase, so still the passage acts as Venturi. But students, when the back pressure is further reduced to a value such that the Mach number at throat becomes unity, okay, such that, so PB is reduced to P0 such that Mach number at throat becomes unity. So it is accelerated maximum such that when it reaches throat, the Mach number at throat becomes unity means the flow becomes sonic at the throat, and but but subsonic elsewhere. So here only m equal to 1, but all other, both in converging and diverging, Mach number is still less than 1 means still subsonic. Okay, still subsonic. So the pressure PB corresponding to that particular value where Mach number at throat become once equal to is termed as PB. At that point will be PB star. PB star. PB star is that particular back pressure value when the Mach number at the throat become unity. Okay. So still the flow is so the passage is Venturi only. It has not become convergent divergent nozzle yet. If it has to become convergent divergent nozzle, the pressure should be reduced to a very low value, and then only the Mach number at exit, the flow should become supersonic. Only if flow becomes supersonic at the exit plane, and this passage can be considered as convergent divergent nozzle. So it means we have to still reduce the back pressure to even lower value, right? Even lower value. Okay, so what should be done? So now after the third case, I am reducing the back pressure to this fourth value. So fourth value, PB is reduced to a very low value called PBD. This PBD is nothing but design value. This PBD is termed as design back pressure value. Design back pressure value. Back pressure value. So I have reduced PB to PBD. So you can see that when the pressure is reduced such, so I forgot to tell you the mass flow rate. Mass flow rate increases with the decrease in back pressure up to third. When third reach means PB equal to P star means the flow is stopped. Flow is stopped means why flow is stopped? Because at a minimum area, throat area, Mach number has reached 1. When Mach is reached 1 at minimum throat area means flow is stopped, and the maximum mass flow rate is achieved. So after that, any further decrease in back pressure value have no effects on mass flow rate. So mass flow rate remains constant after that. So now I have decreased the pressure value, back pressure value to a very lower value called PBD. So PBD means the pressure in the convergence section, pressure is reduced up to throat. At throat, Mach number has reached 1, and since the back pressure is very low, now the supersonic flow will be the Mach number will become greater than 1 in this diffusing section. Sorry, in this diverging section. So now in this case, the this passage has become a nozzle. So before that, it was nothing but before that, this particular region up to this region, it is in a Venturi passage only. But when the pressure is reached to PBD nozzle, so it has become, the passage has become a nozzle, a convergent divergent nozzle. Okay, so this condition can be reached by reducing the back pressure to a very low value called PBD. So it is the design back pressure for the nozzle to achieve full supersonic flow. So in order to achieve full supersonic flow, we have to reduce the value of back pressure to a very low value called PBD, or design back pressure value. Okay, so thus back pressure PB star and PBD are both associated with choked isentropic flow. So you can see here the third and fourth, all this value are associated with choked flow only. Choked flow means at the minimum area, Mach number has become 1. Whenever the Mach number becomes 1 in the minimum area of the throat area, it means the flow has stopped and the passage is no more a Venturi. It has become nozzle. It has started to increase the velocity of the flow. Okay. So, but the higher back pressure PB star, even though PB star and PBD are associated with, so PB star and PBD are associated with choked flow, but the higher back pressure PB star produces subsonic diffusion. So here, even though it has stopped in the divergence section, it is only producing a subsonic. So you can see that M is still less than 1 in case of PB star, but in case of PBD, M is greater than 1. Okay. So even though PB star and PBD are associated with the choked value, PB star produces subsonic flow only, but PBD produces fully developed supersonic flow. Fully developed supersonic flow. So in jet propulsion engines and all, the operating condition is termed as the condition for optimum expansion of the nozzle, that is PBD. So this is the optimum condition. Okay, so reduction in back pressure below PBD. So if I have reduced the pressure below PBD means uh, it has no effect on the distribution of flow parameters with this within the nozzle. Okay, within the nozzle. So in the curve 5, you can see that within the nozzle there is no variation. Same as that of the case in the case of PBD. But since the flow is supersonic in divergence section is supersonic and it is getting rejected to at exit P will be equal to PBD. Exit plane, the pressure will be equal to PBD itself. But since the pressure PB is less than PBD, there will be an expansion wave, because the flow is getting discharged to a lower pressure. Since the pressure at exit plane is PBD, and the pressure at in the outside condition is less than PBD, means naturally there will be an expansion wave, and this particular phenomena is called under expansion. So under expansion, I have already taught you in that in the previous 2-3 sessions, right? I don't remember exactly in which session it came. I think in the previous sixth session, I think. Okay, so this is seventh one. So this is what under expansion means. Under expansion means at the exit plane, the pressure is higher than the back pressure. So naturally there will be an expansion wave forming, and such case is called under expansion. Now, when the back pressure is maintained between PB star and so now back pressure is maintained between PB star and PBD. It's very important. So between PBD and PB star, when the back pressure is maintained between PBD and PB star. So that such curves you can see here: seventh curve, sixth curve, seventh curve, and eighth curve. So these three curves are curves corresponding to back pressure maintained between PB star and PBD. Between PB star and PBD. So what will happen? In this case, normal shock wave occurs within or at exit of the plane. Understood? Normal shock wave occurs within or at the exit of the plane. For example, in the curve 6, you can see that it produces a flow that is supersonic from the throat. You can see that the sixth curve is like that. PB corresponding to sixth curve is you can see the flow comes, the pressure reduces, get reduced like this, and at exit pressure at the throat it will become P star and Mach number will become M1, and again pressure get reduced and velocity get increased, means Mach number is increased, and at particular length you can see that a normal shock. So this is normal shock. This normal shock occurs. A normal shock occurs means a sudden compression wavefront. A sudden compression wavefront. Because why this compression wavefront occurs? Why this compression wavefront occurs? Because since the pressure in this passage is lower than pressure in that particular section, maybe this section be let me put it as A, that particular section A. So this is section A. So PA is less than the PB. Yes, PB, you can see PB is higher than PA. So you are encountering a situation where the exit pressure or the back pressure is higher than the pressure at that particular section. So we have to discharge to a higher pressure. So encountering such a situation means since this is supersonic flow getting discharged into a higher pressure means not possible. So there it means there will be a sudden a steep rise in pressure occurs, and a compression wavefront forms, which is known as normal shock. A normal shock forms. So that normal shock is seen here. So this particular rise in pressure is normal shock, and after normal shock the flow becomes subsonic, means Mach number will be less than 1, and that exit P will become equal to PB. Okay. So any pressure in between this particular in between PB star and any back pressure in between PB star and a particular value called PBE, the normal shock occurs within that diverging section. So this dotted line represents the locus of the shock. So suppose I am taking a pressure here, means the flow occurs like this, and at particular value here the normal shock at this particular section normal shock occurs, and pressure varies like this. And if you continue decreasing PB up to a value called PBE, okay, very important If you continue decreasing PB such that PB is equal to a value called PBE. So you can see here PBE. At PBE, the normal shock occurs at the exit plane. Exit plane. Any PB greater than PBE, or you can I will write better put it like uh, PB star less than PB, sorry, PB star greater than PB greater than PB. So this means PB is a value between PB star and PB. PB is a value between PB star and PBE means the normal shock occurs along can occur anywhere along the length of diffusing section. Sorry, the divergent section. But when the PB becomes equal to PB means the normal shock occurs at the exit plane. Okay, normal shock occurs at exit plane, and there is a steep rise in pressure at that exit plane, and the pressure will at exit will become equal to PB. Okay, now one more case means the eighth case. Eighth case is after, so up to PB. So if you reduce PB up to such that PB becomes equal to PB. So even if you reduce PB less than PB means normal shock, the flow will be supersonic up to the exit plane, but after exit plane, since the back pressure is less than the less than sorry the since the back pressure is greater than the exit plane. So you can see here in the eighth case you can see. So this is the this is the pressure at exit plane. Okay, this pressure is corresponding to the pressure at the exit plane, but the back pressure is somewhat higher than the exit plane. It means again a shock should occur, and this shock occurs mainly. This shock won't be normal anymore; it will be an oblique shock, and a compression wavefront forms, and that this particular phenomena is called uh, overexpansion. Overexpansion. So this is under expansion and this is over expansion. So over expansion occurs when back pressure is in between PB and PBD. Under expansion occurs when back pressure is less than PBD. So this much amount of information, or the process is uh, complex. You will be able to understand if you follow this. If you have correct base, correct foundation, or correct idea of the basics about this particular situation. So hope you have understood the facts I have told you, or the theory of this, the practical, the physical situation that is happening in a nozzle when the back pressure is varied in a convergent divergent nozzle. Okay, so in order to, so I will put this scenario to a very simple form. Suppose this is P, back pressure PB. Okay, this is length of this particular divergent convergent divergent nozzle. So initially back pressure is equal to P0, there won't be any flow. So when I decrease PB less than P0 means slowly pressure get reduced along the convergent portion, and at throat it will become P star. Okay, P star. This is throat area, xt throat area. So now I can divide this particular region. So this is exit plane. Okay, so I'm dividing. So this particular pressure, back pressure is PBD, design back pressure. So we have to reduce PB low enough to make PBD so that a complete supersonic flow is obtained. Fully developed supersonic flow is obtained at the exit. Okay, so this is PB star means, so this value is PB star. PB star means that that pressure which is required uh, to make the flow choked. So at this, when PB is reduced from P0 to PB star, the flow gets choked for the first time when it reaches PB star, and an intermediate pressure PB is such that the maximum back pressure required to get the normal shock at the exit plane. So in between PB star and PB means normal shock won't occur at exit plane, but it may occur in the section, any section anywhere in that divergent portion. In between PB and PD means there will be an under expansion. Below PB, sorry, in between. So here it is over expansion. Over expansion. Below this, under expansion. Under expansion. Okay. So hope you have understood this concept, and I think we should do a problem. Problem I will give you as a note, and don't worry about it. With this, I will stop this particular session. Thank you.